whenever we heat a solid object, any solid object, whenever we heat, it changes the color. Actually, what is happening behind this? When we heat a solid object, it absorbs that heat, it absorbs that radiation within its structure. And after some time, when its absorption limit is reached, it emits those radiations, right? You have often seen the glowing solid objects. You provide heat, or you put an object on fire. It will absorb that heat, and after some time, it will radiate that heat in different ways, right? So whenever we heat a solid object, it glows, right? And if we change the amount of heat, we increase the temperature, then the colors of the solid objects changes. Sometimes you see that whenever you put an object on fire, it changes its color to red, normally, right? And sometimes whenever you apply more heat on that object, on some melting blonde or on some such an object which have a lot of heat, for instance in plasmas, have you ever seen? Then you will see that the color of that object will change to yellow after reddish color. Once you heat the object, it will change the color to red. Then after much amount of heat, then it will change its color to the yellow. And if you even more apply heat, large amount of heat, then the object will change its color to white. So there are various changes of color in the object by the application of heat and temperature differences. This is the characteristic of solid object, and this is actually the emission of radiation from the solid object. Means the solid object once absorbs the heat, and whenever we apply a large amount of heat, after a certain absorption limit, it will emit radiations. So this is a simple phenomenon you have often studied in daily life. But what was the problem? The problem was that for various solids, we have a range of absorption energies and range of emission energies. Right? Means some solids absorb the heat in ultraviolet region, some other solid may absorb heat in the visible region, some other solid may absorb the heat in infrared region, and so on. There are different frequency regions. So, problem was that we have to study the different solids, the various solids for different energy ranges. So scientists thought that to study this phenomenon cumulatively, consolidatedly, at the same time, if we want to study the whole energy range, then we must have an object which absorbs the whole radiations, all radiations falling on it, irrespective of the range of their frequency, whether they are ultraviolet or infrared or visible. What I'm saying, I am introducing actually Blackbody to you as well. Blackbody is an ideal object, idealized object, which absorbs all radiations falling on it. And when this blackbody is heated, it emits the whole radiation. So you can think as that blackbody is an ideal absorber and ideal reflector. Ideal absorber means it absorbs the whole radiation falling on it, all types of radiation falling on it, and it emits all types of radiation whenever it is heated. So this is the basic definition of black body. And why a black body was constructed? Black body was constructed because scientists who wants to study the whole energy range at a same object, right? Because different solids absorb different ranges. So it was not possible for the physicists to study all energy range for a single object. So they studied ultraviolet for another object, infrared range for other objects, visible range for other objects. So that was not a compatible way of comparison of theory. So they first constructed a black body, and black body was constructed in such a way that they took an object and make a hole in that object, a very small hole. You can say that this is a cavity with internal walls with black color, with a coating of a black color. So it will perfectly absorb the whole radiations. Once the radiation you put on the whole of that cavity, and that cavity takes the black body radiation inside, and once the radiation comes inside the black body, they are being absorbed around various walls of the black body. They collide with the walls, and the walls have the capacity to absorb all those radiations. And once the radiations are trapped inside the black body, right, then if you heat the black body, it will emit those radiations. So no radiations is reflected from black body. This was our story of black body radiation. You know, energy density of black body radiations with respect to frequency. This plot is known as spectrum of the black body. Right? Energy density is the energy per unit volume per unit frequency. Like joule per meter cube per hertz means energy per unit volume per unit energy. Right? With respect to frequency, the curve of this energy density is known as spectrums. The level of frequency, right? Here the level is around 1, and here is the level around 1.5, and here the maximum point corresponds to 2.5, and here the maximum point I think corresponds to 3. So you can see that the maximum of curves changes with the increase in temperature, right? So if the maxima changes at various frequencies or various temperature, it means the color of the object changes, because color is related with frequency, right? Red color has its own frequency, blue has its own frequency, white has its own frequency, right? So this was the reason of change of color when you heat the solid object. So the whole story and the spectrum was plotted experimentally. Now it was the theory turn to satisfy this spectrum. Theory must satisfy the experiment. Theory must be related with the experiment. If it doesn't relate with the experiment, then it means there is possible error in the theory or in the experiment, right? So what is the way to improve the experiment? We can repeat it with certain conditions and improve that errors and uncertainties. But for a repeated experiment, if it does not consist with the theory, then it means there is some problem in the theory. So the same situation was here in the black body spectrum. This experimental spectrum could not be explained with the help of that theory of classical mechanics, classical thermodynamics, classical statistical mechanics, etc. So scientists was wondering that why this spectrum cannot be reproduced with the help of theory. That was the black body radiation problem. you will understand the problem, then we will move towards the solution. If we don't know what is the problem and we are explaining the solution, then it is useless, right? So, first of all, you must have to understand that what was the problem of black body radiation that was not being explained by the classical physics, and that was a dilemma for the classical physics. So that is very important. First to define the problem and then to find a solution. Okay. First of all, some physicists in the era of 1800, mid 1800s, mean 1850s, right? Many of the physicists have experimental data and they plotted the plots like this. But the theoretical physicists could not explain the spectrum at that time. They tried various techniques, like one of the problems was explained by Wien's energy distribution. Wien's law. Wien tried to explain this black body radiation spectrum, and he introduced a law known as Wien's law. Wien's law was given by energy distribution equation based on Stephen Boltzmann law, right, and Maxwell distribution. So, Maxwell distribution, as you know, is a classical distribution of the particles, and you know this is an exponential decay, e raised to power minus beta nu over T, where T is, you know, absolute temperature. So this factor known as Boltzmann factor was introduced for the distribution of this energy density of the black body radiation. And at the same time, he introduced frequency Q by various empirical parameterization. I couldn't explain to you at this time the experimental parameterization because this is a deep concept and we have to consume too much time for this concept. So I will simply tell you that this was the formula introduced by the Wiens for the description of black body radiation at that time in 1894, I think. Right. So this formula was plotted theoretically, and its plot was like this. The dotted line, as you have shown here, right? This dotted line shows the Wiens curve. Okay. So Wiens curve was consistent with the experimental curve for a higher frequency. You know, this is very close to the experimental values at these higher frequencies. You can say almost above 5 hertz frequency, right? So at this range, it is very close to the experimental data, but near 4 hertz, this deviation increases, right? This deviation, as you have seen from this graph on screen, this deviation is going to increase, and as you move downward to the frequency range, this curve is going upward for the higher value of energy density. So there is a mismatch for lower values, and there is a little bit match for higher values of frequencies. So the Wiens law is partially successful and partially not successful. It has its pros and cons as well. So the pros of the Wiens law is that it is useful to explain black body spectrum for higher frequencies. And the cons of the Wiens law is that it fails to explain the black body spectrum for lower frequencies. So you can say that it is successful for higher frequency, but it fails for the lower frequency. So physicists was thinking that why this Wien's law is failed for lower frequency. It means there is some problem inside the theory that considered by Wiens. There is some problem in the classical physics, and that's why it's not explaining this experimental study. Then afterward, Rayleigh and Jeans, these are two names, Rayleigh and Jeans, two different names, and they collaborated and found another way by optical waves calculation. This is the number of waves depending on the frequency, and they thought that the energy density is the product of number of waves, number of modes of the standing waves inside that blackbody radiation, and in average energy of each mode. So this is number of modes 8 pi nu square over c cube into average energy, and average energy they calculated from Maxwell-Boltzmann distribution. This is E into e raised to power minus e over kt dE over e raised to power minus e over kt dE. And if you solve this integral, the answer will be kT. Means the average energy per mode will be kT. You possibly have derived this equation in B.Sc. If you multiply this 8 pi nu square over c cube with this average energy kT, you can write this Rayleigh and Jeans law. And if you plot this Rayleigh and Jeans law, it will follow like